So our project is a work done by a solar-powered RC car using supercapacitors. And Sameem, Chris, Jeff, and our advisor is Dr. Rachel. This is basically our agenda for what we're going to explain today. We're going to tell you what we did, the results, how it worked, all of that. The introduction, basically give you an idea of all the things that went into the car and how they work, and how they should work, and how they do. Some of our results, basically the work that was done, the work that was done by the car, how it operated, how it moved, etc. And the results, the cost of everything that went on to this, and alright. Basically we designed this car as sort of an educational tool. Since we were using solar panels, we figured we'd make something that would introduce solar panels to kids and basically get them started on alternate energy and get them acquainted with things like that so they can at least come up with things for the future. And also it's an educational tool and it's sort of a toy, so they get both sides of the coin by having something an RC car to play with and also learn about solar energy. And this one will be a little bit tough for children to understand, but they also have supercapacitors, so the older kids can get acquainted with electrical engineering. Alright. Basically, we wanted a configuration that would only work with solar energy. We didn't put any batteries or anything like that in there. It's basically a solar panel and goes straight to the supercapacitors. And it can move back and forth on flat land. We also wanted it to go up a ramp because that would require a lot more energy to do. So it added another dimension to the project. And then, like I said before, we're measuring how much work is done by the car.
These are some of our results. So in order to know how much energy was required for the RC car to go up a ramp, we needed to know the mass of the car and as well as the height. And then to measure the amount of energy we actually consumed, we had to measure the voltage across the capacitors before and after going up the ramp and using 1/2 CV squared. So the energy required should be close to the amount of energy used, and any extra energy used would be due to power loss in the drivetrain and electronics. Here we have our data measured in both joules and milliwatt hours, and we actually calculated the efficiency, and our system is about 79.4%.
So this is the basic setup for the project. Basically everything leads to something else that eventually makes the car move. At first you have the solar panels, which we had 6 of, and I'll bring it out right now so you can see. We had 6 thin film panels right on top, and that's basically what absorbed the sunlight. And that went into a 5-volt regulator, which all the components you can see back there. We use a 5-volt regulator so that the components of the car won't completely burn out by all the energy that's absorbed. And that energy went into the supercapacitors, which stored all the energy for us to use for whatever we decided to. And that energy is used by the receiver, basically the controller for the car, remote control car, and sends radio signals to the speed control, which then translates into the motor, makes the car move. So everything basically leads to something else to make the car eventually move. And let me explain the panels a little bit. They're thin film polymer. As you can see, they're about as thick as a business card. They're even flexible, as you can see up there. They have photovoltaic cells. That's basically what absorbs the sunlight. They're made of silicon semiconductors, absorbing the sunlight, and then sends it as electrons, and that's basically what creates the current. And it actually creates its own electric field to control the flow of the electrons, which obviously creates the power used. So that's basically how the current is created by the solar panels. I'm going to go a little bit into detail on the controller. Basically, that's exactly what it looks like. It's your regular RC car controller. It controls how much acceleration you want for the car. So the more you press it, the more you get. And the more acceleration, the more energy it will use up from all the energy stored in the capacitors. That sends a radio signal to the receiver, which is in the car. The receiver takes those signals and translates it to the motor, makes the car move. Pretty simple concept. And the motor, I'm going to go in detail about the motor and explain it to you. It's a brushed DC motor, which means you're going to have two magnets. Each one, you have the north pole of one, south pole of one. Then you have an electromagnet in the middle. And then a commutator around the electromagnet with two slits. And those two slits help change the current of the electromagnet, because you're going to have two brushes on each side, so that as it's spinning, and it gets to a certain point, the brushes would hit it, changing the current in the electromagnet, basically changing the poles of the electromagnet, so that it continues to go. So it gives you the motion of the motor. And the reason why we use a brushed DC motor is so it's lighter, and that's the one that came in the car. Basically, that's how it powers the motor, a little bit of electromagnetics. And supercapacitors, these were the other huge key of the project. The difference between supercapacitors and capacitors is pretty large. Regular capacitors have the metal plates and dielectric. Supercapacitors don't have necessarily a metal plate, they actually have activated carbon, and it creates their own dielectric when it's charging. So when it's charging, the activated carbon creates a double electric field, which makes the dielectric for the supercapacitors. And as you're charging the supercapacitors, you're creating an ion absorption layer on the active carbon. And that's basically how you get your charges. And since carbon has such a large surface area, you can harness a lot more power in these supercapacitors than you do with regular capacitors. That's basically the main reason why you would use a supercapacitor, because you want to harness a lot more energy than with a capacitor. And that circuit that I use there is just basically to explain how long it takes to charge the supercapacitor. You can sort of look at it as an RC circuit, a bunch of RC circuits in parallel to represent the ion layer on there. And the RC current constant it takes for all this to charge is how much it would take to charge the capacitor.
So, in our initial design, we had to use physics to calculate the amount of energy required to climb up the ramp. We had to assume an amount of mass and height of the ramp, and then convert that into joules and megawatt hours, which came to be 5.2 megawatt hours. In our initial design, we used 4 solar panels from Genco Electronics, which were actually manufactured by Aerofield Incorporated. They were actually rated at 7.2 volts and 200 milliamps each, but when we characterized them, their open circuit voltage and short circuit current reaches as 11.96 volts and 233 milliamps. So we actually had to use a 5-volt regulator so as not to destroy the RC circuitry. We have 8 1-farad supercapacitors rated at 5.5 volts each, in parallel with 3 10-farad capacitors with rated voltages of 2.5 volts in series. And sadly, only with that setup, the motor only turned on for 16 seconds, even at minimum throttle. So for the final design, we wanted to increase the amount of capacitance. So we actually calculated an amount of energy needed, and then we found the capacitance using the FCD squared again. And then we found the number of 10-farad capacitors to be required because they had more capacitance, which was about 12 capacitors. Even then, We added 2 more solar panels because we wanted to lower the charge time and increase the amount of power delivered to the motor. And so now there would be 14 10-farad capacitors in parallel with the 1-farad capacitors with 2 capacitors in series per branch. And we actually added balancing resistors across each series capacitor. Here you can see our circuit diagram for the final product. We had increased capacitance to 43 farads, and the balancing resistors across each capacitor were added so they create a voltage divider that controls the voltage sharing amongst the series capacitors. Without them, some capacitors may be overcharged and some may be undercharged, which can destroy the RC circuitry.
We're talking about the buy design. Basically, our main objective for the design for the buy was to make it light so that it can climb up a ramp easily. It had to be less than 3 kilograms according to our specifications. It also had to be sturdy so that when you're using it, it doesn't fall apart. It also had to be big enough to fit all 6 of these panels on it. As you can see. Each panel is about 24 centimeters by 14 centimeters. And the whole configuration is 49 centimeters by 43 centimeters. So our first design, we wanted to use a plastic storage container lid because it was light, obviously. And it was big enough to hold the 6 solar panels. But the downside to this was that it was easily bendable and flimsy. We went ahead and drew a model of it. So basically, we would put a motor in the middle, and then we would drive the wheels using a four-wheel drive traction, using some sort of drive configuration that we built. So we went with design 2, which was using a wooden board instead of the plastic easy lid. That weighed about 1 kilogram, which is still within our specs. And it still had the area to fit all those solar panels on top of it. And it was strong and rigid, so it wouldn't break while you're playing with it. But we went ahead and built it. We had difficulty constructing a drivetrain that would be efficient because we didn't know how to connect the ends to the wheels and the differentials, which is what we did. And we were facing slippage, and we were looking for because of that. So we went ahead and designed another design, which is our final design, which is right here. It's called the Soulstice. We use polystyrene poster board that you can use for presentations. It's really light material. The dimensions of the total design is 60 centimeters by 48 centimeters by 19 centimeters. And the total weight is 2.45 kilograms, so it fell right under our specifications. So you can see this is the compartment. We held the RC circuitry. And we have a little panel on top, so we can access the car in the motor if something happens to it. Here's our capacitor configuration here. And we attached wheels to the back. They're stationary, but they're not linked to the drivetrain or anything. They're just there to support the back. And that kind of added friction to our design, so we had to give a little kickstart through ground when we were testing to overcome that friction. And I'm going to hand it off to Chris who can explain the test setup.
Okay, so since our physics calculations assumed the mass to be constant mass and constant acceleration, there's actually a discrepancy between the actual amount of height travel. So we had to calculate that. iron the ramp with the solar panel off. Here's a little animation that we played to show you what we did. Yeah, so you can see initially it was 5.05 volts and it dropped down to 4.6 volts. And that's actually just another slide just to show in case the animation failed to play. So from there, we calculated the amount of energy we used and the amount of energy required and wanted to compare them. And here's
5.05 volts in the capacitors, and we are taking off the solar panels. We're going up 6-inch ramp, 6-inch ramp with 50% drop, 6-foot ramp, 6 inches high, with 50% throttle with a slight kickstart.
That was about 2.5 seconds.
Let's check the capacity. Yeah. 4.68 volts, and we see that the solar panels are still disconnected.
Alright, so here we calculated our results, and we consumed about 0.8 kilowatt hours, and we compared it with our required kilowatt hours, 0.6.9, and we reached an efficiency of about 79.4%.
Should we have time for questions? Okay, I'll do it really quick. This is how much we spent. This is how much we spent again. And room for improvement, more efficient speed control, maybe make it have more panels, more power. Conclusion, RC car works, supercapacitors, it went over the ramp, we could even move wherever we wanted to go. And the efficiency, which Chris just explained, and acknowledgements, Professor Reichel, Scott, Ryan for the parts, RC Limited for the car, Jacob for the solar panels, and that's it. Yes?
Where did the capacitors come from?
Japan. They don't have them here, we have to order them.
From Japan?
Yeah, from Jacob, we should pick them up.
Oh, Genco, okay.
Is 10 farads, if you had a 10 farad capacitor, which was not a supercapacitor, how big would that be with using a standard capacitor? How big is a regular 10 farad capacitor? Is that a big capacitor or a little capacitor? How big do you think a 10 farad capacitor would be? Can you buy a 10 farad capacitor, regular technology? How big would it be? As big as a podium or not?
Probably the size of this room, probably the hall.